Okay, so far we have seen that policy constraint methods can be effective at offline RL, but they are limited because they require estimating the behavior policy and they can often tend to be too conservative. So we next sort of ask ourselves if we can do better or we can develop better methods for offline RL. In order to do so, let's revisit the motivating example that we started off with, and let's take a slightly different perspective on this distributional shift problem that we have been discussing. So the motivating example was this plot of an actor-critic method on the half-cheetah environment when trained with only expert data. And here we saw that the algorithm performs very poorly. It gets like a negative return, although the expert has a positive 10,000 return. And it overestimates the Q values, which is the estimate of how well the algorithm thinks it is doing. So can we directly tackle this false overestimation issue in the Q function instead of trying to fix or trying to avoid auto distribution actions in the back? So far the policy constraint methods constrain the policy, but can we directly kind of try to tackle this overestimation issue where our notion of Q function, notion of value of the policy is in a sense lower bounded? And the reason behind why we want this, just to reiterate from the previous slide, is that in some cases, not all auto distribution actions are bad. Auto distribution actions are bad only when they affect the policy and when they lead to poor performance. They're not otherwise bad. So in this part of the lecture, what we'll do is we'll devise methods that learn lower bounds on the policy value or the policy performance. And when I refer to policy value, it means the technical term. It technically refers to the value function of the policy. And turns out that there are two ways of doing this. One kind of way of doing this is a model-based approach, and the other one is a model-free approach, similar to how there are two ways, or similar to how model-based and model-free RL methods work. And we'll discuss them one by one. So let's start with the model-based family of methods. Let's first discuss what's a broad framework for doing conservative model-based RL, and then we'll go into some specific algorithmic instantiations that have been done by researchers very recently, which fall into this framework. So in model-based RL, typically you learn a dynamics model for the MDP that you're operating in, and optimize the policy against this dynamics model using planning or Dyna or some other model-based algorithm. In this offline model-based RL methods, the framework, or in this conservative framework for offline model-based RL, we'll have an additional bit that is marked as the PMDP or conservative or a pessimistic MDP. And our framework would basically be that we train a dynamics model from the offline dataset given to you. And now what we'll do is we'll make the reward function be conservative. So the reward function that we'll end up using for planning or for model-based RL training would end up being a lower bound on the actual reward function, and hence it is in a sense conservative and would give us lower bounded values for the policy. And the policy optimization part would just be as it is done usually with model-based RL, for example, via planning, Dyna, or any other method. So to get intuition for what this reward function or what this conservative estimate for the reward function actually means, let's look at this sort of nice cartoon from this Morel paper from this year, which depicts the state action space of the MDP as this parallelogram that you see on the slide. The green regions of the parallelogram are regions which the state are regions of the state action space that are actually seen in the data set. So these are the points, and the blue points are the points that we actually saw in our data set, and the green regions is sort of like a relaxation of these points. And the region marked in the brown color and denoted as U is the unseen region. So that's a region which you haven't seen in your data set and does not lie in your data set support. Now what you want to do here, or one way to get conservative reward functions is to keep the unaltered reward function, a reward value, for the points that you have seen and they are within your support, and modify the reward to make them be pessimistic or be lower bounded on unseen things, or unseen parts of the state action space. Now, if you imagine what this would do is, if a policy were to, if you execute a policy through the state action space and compute its reward under this modified reward function, it would be a lower bound because you are either preserving the original reward or you are down, or you are making it be pessimistic. So in a sense, the value of the policy can never be higher than what it is on the actual MDP, And so you're kind of guaranteed to learn a lower bound on the policy value. So what are some typical instantiations of this model-based conservative framework? So typical methods, or there are two methods actually that we'll discuss today. And these both of these methods, what they do is they do additive transformations on the reward function to make it be pessimistic. So for instance, they would they would do model-based planning or model-based optimization under a reward function r tilde, which is the original reward function minus lambda times a function USA that depends on that is basically the pessimism or the conservatism that you add to this reward, to the original reward. One of the methods that is model-based policy or model-based offline policy optimization, which is MOPO, what it does is that it maintains an ensemble of dynamics models, and the dynamics models are probabilistic, so they are a Gaussian distribution parameter with mean mu and a covariance matrix sigma. And what it does is that it computes the maximum value or the maximum norm of the covariance matrix across the ensemble. So that's this max over I going from 1 to n of the norm of sigma I at that state in action. And now this norm, if this value is high, what it tells us is that we do not know, or it tells us that the dynamics model is not great at modeling the dynamics at a particular state, implying that it is implying that that particular state or that particular state action pair might lead you to states which are unseen. So the next state for Sj and Aj might be an unseen state. And so what it does is that it subtracts this value from the original reward function. So it computes a new modified reward function that is the original reward function minus this norm of the covariance matrix. Whereas if the MDP, if you had seen the corresponding transition, this covariance matrix were to be small, and so you would not subtract this value. And then what it does is that it uses MBPO or a dynastyle algorithm to do the model-based planning part. The second method that we'll cover is the Morel approach, which is similar to MOPO in that at the high level, but it is instantiated in a very different way. What it does is that it still trains an ensemble of dynamics models, but these are all deterministic dynamics models. So they are deterministic mappings from state comma action to the next state. And now what it does is it computes a disagreement between these different elements of the ensemble using just the L2 distance between the predictions of the dynamics model I and dynamics model J for a particular state action pair. And if this disagreement is too high, it means that you have not seen a particular transition SAS prime in your dataset, and so you are kind of uncertain about it, or that transition is taking you outside of what you have seen. Now, rather than subtracting it directly from the original reward function, what it does is that Morel modifies the reward to be directly equal to the minimum reward you can get on the MDP, which is negative of R max, provided this sort of disagreement metric is more than a given threshold. So it's sort of a more step function like behavior with Morel, whereas MOPO is a bit more continuous. And then what it does is that it uses simple planning to optimize for this reward function. Okay, so how do these methods perform empirically? So turns out that even if you do not correct the reward function, so even if you do not add any conservatism to the reward function, model-based offline RL methods can work well with datasets which have broad coverage. So if you do not have that much distributional shift, turns out that these methods can perform quite well. And the reason is because you can learn an accurate model generally when you have enough coverage. And now you can perform you can kind of plan in that model and train your method. Whereas typical of policy RL methods, which are model free, may not be able to perform well here because sort of limited data and due to like somewhat unseen actions. Now, next we sort of compare the performance of MOPO here, and Morel also has strong results, and you are encouraged to go and check it out. But these results were taken from the MOPO paper, and what we find here is that conservatism helps in situations with narrow data sets. So compare MBPO, which is the model-based RL part of MOPO, and compare that to the MOPO algorithm, which is shown in the table. Find that on the medium data sets, which are data sets generated from a single policy that is a mediocre policy. Turns out that MOPO is quite good as compared to MBPO. It's much better actually. Whereas in other cases, the difference is not too large, or even MBPO performs quite good. Finally, if you look at the numbers as a whole, you'll find that model-based offline RL methods, or MOPO in particular here, ends up performing much better than policy-constrained methods BEAR and BRAC. And obviously, those methods also perform better than naive of policy RL, which is indicated in SAC. So that suggests that basically taking this different approach of conservative modeling can actually perform better than policy-constrained methods in a number of these scenarios. Especially note the performance difference on the medium expert data sets, which is somewhat hard for policy-constrained methods to model in general. Okay, so next we get to the model-free variant of learning lower bounds. So in this algorithm, which is the conservative Q-learning algorithm, our goal is to learn lower bounds on the Q values. So without having a dynamics model, can we directly lower bound the Q values using an objective? So the model-based method, what they did was they relied on lower bounding the reward function and using a model to unroll the policy to be able to lower bound its value. But here we do not have a dynamics model. Here we only have a Q function and we want to learn a lower bound. So one way of doing this, which the conservative Q-learning paper does, is that it augments the standard Bellman error training of the Q function with an additional regularizer, which I will refer to as the CQL regularizer. And this regularizer, what it does is that it minimizes the large Q values at a particular state S. So it finds out a distribution mu, which puts most mass on those actions for which the Q value is super large, and those values are minimized by the Q function, as you see in the objective here. What you can show as if you do this, if you train your Q functions using this objective rather than the standard Bellman error, you can show that the resulting Q function Q hat by CQL lower bounds the actual Q function Q pi, or Q, which is denoted as Q here. And this is true on all states that you see in the data set, as well as all actions on those states. And now what you could do is basically plug these conservative Q value estimates into a standard actor-critic method that tries to optimize these values, or tries to optimize the policy against these learned Q values. And these learned Q values are, or learned conservative Q values are estimated using the offline data D. We'll call this CQL V1 because there's a second version that we'll discuss next that is in some sense better than this version, and that will be the version 2 of the CQL algorithm. So turns out that when you minimize the Q values here, your Q values can be super can end up getting too low in magnitude, because you just sort of like the minimized big Q values term is just sort of a linear term that pushes down the Q values everywhere. So can we do something better? Can we get a tighter lower bound? Turns out that we can. So we modify the CQL objective from the previous slide to now have an additional term. So we still have a term that minimizes big Q values. We still have the term that minimizes standard Bellman error, but we have an additional term that maximizes the Q values on actions sampled from the dataset. So we are saying that you want to push down everything that you've not seen. We want to pull up the Q values on the dataset, and we want to minimize the standard Bellman error. So those are the three terms in the objective here. It turns out that if you optimize and you find a Q function using this objective, it's no more guaranteed to be a pointwise lower bound on all states drawn from the dataset and all actions, as we saw with CQL V1. But a good property which still holds is that the value of the policy, or the value function of the policy at a particular state S under this learned Q function. So if you compute the expectation of the Q value under actions drawn from the policy, pi, which is denoted as pi k as well, you will find that that value is still a lower bound to v pi of s. And this is true for all states in the dataset. So we get a slightly weaker guarantee for the lower bound, but this is also in a sense tighter because we're not underestimating all Q values arbitrarily, but rather we are saying that there are certain Q values that are overestimated, which is the Q values in the data, certain Q values that are underestimated, which is Q values at unseen actions or mu, but the overall value of the policy is still going to be a lower bound. The algorithm still remains the same, learn Q hat by CQL using this version of the CQL objective, and optimize the policy using a standard active critic update. And we call this CQL V2. So what's a practical CQL algorithm? So we saw that sort of the objectives that we looked at so far consist of this mini-max problem where you're minimizing a quantity with respect to Q and you're maximizing something else. In both cases, it's this distribution mu. But can we kind of avoid this maximization to some extent to be able to make the algorithm simpler? So it turns out that we can, and the real way to do it is to add a separate regularizer that you see on the bottom left of the slide to the optimization problem that we saw. And this regularizer kind of can be thought of as a penalty to smoothen out the inner maximization without any loss of like guarantees on the lower bound. And when you solve for that, and more details are there in the paper, which I encourage you to check out, we find that we get a very intuitive form for the algorithm that looks which optimizes the Q function against this objective that you see there on the slide. What it does is that it pushes down, rather than pushing the maximum Q value, it pushes down a soft max or a log sum x of the Q values, pulls up the Q values drawn from the behavior policy pi beta, and minimizes the Bellman error. So very similar in spirit to what we saw, except that there's a soft max rather than a hard max over here. In order to implement this algorithm, we still do it the active critic style, just change the Q function update to use the CQL objective, which is shown here. And that's the standard change on top of deep Q learning or active critic algorithms that we would want to make. Okay, so how does CQL perform empirically? So we first compare the learned policy value. So learned policy value to the actual policy value for CQL. So for model-based methods, because we were directly altering the reward function, it was kind of almost clear that the learned policy value will be a lower bound than the actual policy value. But what is the case for CQL in that sense? So here we are directly aiming at learning the Q function, and therefore this question is a valid question to ask. So we compared the learned value minus the actual policy value across 3 domains, and these are three different data sets that you could use for training the policy, or use for offline RL. And I'm not going into the details of what data set we are using here, but I'll tell you where exactly these data sets are borrowed from, and I'll encourage you to check those out. But the high level bit really is that CQL and CQL variants, so CQL equation 1 is CQL V1, CQL H is the V2 version, both of them learn lower bounds on the policy value because this difference is negative, whereas all other methods do not quite learn that, and all other methods like ensembling methods or even a policy constraint method like Bear do end up overestimating the policy value. Next, we compare CQL to prior policy constraint methods on some of the harder tasks where we saw policy constraint methods do not work, such as the ant maze task. And we also compare it to behavior cloning, standard of policy RL, and policy constraint methods. What we find here is that in tasks where we saw policy constraint methods fail drastically, for example, in these medium ant maze or large ant maze tasks, we find that CQL is able to perform quite well, and it gets a non-trivial improvement over these methods. And this is not possible without the stitching property that we discussed at the very beginning of the lecture, and this hence shows that CQL is efficient at stitching. We also compared it to these prior methods on some hand manipulation tasks where you have a robotic hand, you want to control it to solve certain tasks, where it did perform better than other methods. It was not the best in all cases, but certainly very good. As well as on a domain where we have to solve a sequence of tasks in a kitchen environment to be able to solve a long horizon compositional task at the end. And here we found that this CQL is the only method that can outperform BC, and some policy constraint methods, for example, BRAC, do not even work. Okay, so to summarize, we have covered 2 classes of offline RL methods so far. We've covered policy constraint methods that work well, but they are conservative and require behavior policy estimation, which may not be the most desirable thing to have. And we also covered model-based and direct Q-function-based algorithms for learning lower bounded policy values, which generally perform better since they're conservative and do not require behavior policy estimation, because everything can be done using samples, and everything is done on either or altering the reward function or the Q function. What we'll do next is we'll cover some related problems. So problems that are not offline RL exactly, but somehow very related. And we'll also discuss how we should evaluate offline RL methods and some practical instantiations of these methods towards solving dialogue and robotic manipulation problems.